Hello everyone. In today's lecture, I'm going to talk about digital design considerations, the integration, the timing, and asynchronous interactions. Before we get into the details, at the beginning of this course, the first 3 chapters has shown us the foundation of the logic design. Binary numbers, arithmetic operation with the binary numbers, conversion of the binary numbers, and Boolean expressions for simplifications, sum of product, product of sum, canonical standard forms, Carnot simplifications, min terms, max terms, and so on. Then on chapter 4-5, we have seen design and analysis of combinational circuits and then sequential circuits accordingly. We introduced the flip-flops and also latches. Then on chapter 6, we have gathered together these flip-flops and the latches, and we can form registers and the counters or the shifters. So as you can see, we are building up from the foundation to the logic level design or gate level design, then the logic blocks, and then we went one level up with the controlling the data path using finite state machines, which we can derive algorithms, hardware algorithms for running the data path. Now, while we are considering all these together, we also need to consider some other things that are related with the digital design. That's why we have got these digital design consideration chapters. Let's start with the integration part. So, if you do remember from the first chapter, we said that we are working with zeros and ones. And I ask you about why are we working with zeros and ones, and we have found a solution that because we need to turn on and off, and that turn on and off is coming from switches, and those switches are in electronic circuits. They're known as transistors, and we have said that these transistors, starting from 1960s, they start to get shrinking down, and can integrate more and more on these into one chip. So the amount of integration is actually nowadays is around billions of transistors inside of a microprocessor, and this is coming from Moore's law, where it states that the number of transistors inside of a chip will double every 18 to 24 months, and that's what's happening. And we are now in the nanoscales, and we are actually running to the atomic levels. Now this is all part of the integration because we are putting more and more transistors, more and more functionalities and resources inside of a chip, and these chips are generally taken out and mounted on a board, on a PCBs. It can be an FPGA, microcontroller, microprocessors, and so on. They have their own sockets and their pins which are attached to the PCBs. Now then we can also describe this integration with their levels. So for example, if you are building a logic circuit with only less than 10 gates, we can say that that's a small integration. Or if you are building a 10 to 100 gates, that can be a medium scale integration. Large scale integrations, hundreds to thousands of gates together, and then very large scale integrations, which we are now using on most of the systems, is thousands to billions of gates altogether. And you can see some examples like logic gates, adders or decoders for medium scales, the large scale small processors or the memories, and very large scale, which we talk about complex processors on FPGAs and so on. And this is all part of the integration, and that integration comes from the transistors. And in today's technology, we are using these 2 types of transistors, which is known as PMOS and NMOS. So this is coming from the altogether from complementary metal oxide semiconductors. So complementary means the PMOS and NMOS, they are complementing each other. When one of them is on, the other one is off, and so on. So they are complementing each other, and when we build them together, they can form any kind of logic circuit. So the technology that we are using is known as complementary metal oxide, which is the most used technology. Nowadays the researchers are looking for an alternative ways of implementing these designs because they want something faster and power efficient and also accurate when they perform any logic operations. Now the next thing that we need to consider, apart from the technology itself, in the digital design, maybe I also mentioned that before, but we need to consider the number of inputs available on a gate. So for example, we have got a gate and we have got lots of inputs coming into one gate. This is not an efficient way of implementing a logic circuitry. This is known as fan-in. So fan-in, it's limiting its high-speed technology, and we have to be careful how we are going to design the circuitries. So rather than having tens or hundreds of inputs to one gate, we might try to have a couple of inputs, and then you can integrate it with another input and more. So this is actually increasing the number of stages in the logic design, but it's actually helping with the speed of the technology. So if you're not worried about the area of the circuitry, fan-in, we can be careful with the fan-in, and we can design a multi-stage circuitries like this. So this issue is known as fan-in, and when we want to consider the digital design, we have to be careful with the fan-in side of it. So it's affecting the speeds, so we need to be careful over there. Like a certain CMOS technology may limit NAND fan-in to 4. If you want to have a 7 input NAND, then you can use 4 plus then another 4 inputs, so that you can have 7 inputs together. And they're both, on these designs, they're both having the same logical expressions, but the left one is much better, as we are not having a large amount of inputs to one gate, and this is important. We also have the same or similar stuff with the output of a gate. So for example, you have a gate with 2 inputs, but that gate has to derive multiple outputs, and this is also a problem because these are actually representing an individual load, and each individual load means we might have, let's say, logic 1 over here, but that logic 1 will be degraded because it has to drive 5 or 10 outputs together. This is not going to help that gate to drive it. It's not gonna drive those large amount of loads. So this is known as fan out, and we need to be careful on that as well, because otherwise the performance is going to be degraded and it's not going to be acceptable. So what we can do, again, with the fan out, we can derive the logic expression with small circuitries, and we can add buffers or inverters for each line so that we can allow signal to not to be degraded. So this is a implementation for the fan out. Rather than having an individual lines, we can add inverters and buffers over there, and we can reduce the fan out problems. And it says the maximum fan out of CMOS gates are set based on maximum allowed load capacitance, which sets the maximum transition time from high to low and low to high. So it's about the charging the capacitance over there. Then we have got another parameter in digital design consideration, which is known as noise margins. Now, I don't know if you do remember, when we have something like this as a logic levels, we might have some problems with this. So what are those spikes? This is actually noise. And if you think about it, let's say our transistor turn on point is somewhere here. Okay? So if the transistor's turn on point is, or the threshold voltage is somewhere there, at this point, or maybe there, or maybe somewhere here, as we were expecting valid logic 1, or maybe 0 over here, we are not going to get that. Because of the noise, these spikes, actually it might turn off your transistor, or it might turn on your transistor as it is above or below the threshold voltage. So noise is really important over here, and we need to be careful when we want to design digital circuits. So we have to have a noise margin which our circuit can tolerate to these margins, and without having any problems we can have a perfect outputs. Otherwise we won't have valid logic levels and it might not be functioning properly. Then another important metric is the propagation delay. So propagation delay is when you have an input on a multi-level circuitry. If you talk about a typical combinational circuit, let's say I have got a AND gate, then another AND gate, then OR gate, and then we have got a NAND gate. Now each of these gates have their own gate delays. So let's say this is 2, this is also 2, this is 3, and this is 1, for example. Now each of these gates have their own individual gate delays, and now what we are expecting is, if I fire in an input from here, from point A, and I want to observe the output on point F, so what will happen over there? I need to go from 2 plus 2 plus 3 plus 1 gate to have output F. So this is actually going to be 4 plus 3, 7, 8 gate delays. This is actually showing me that my A is going to appear on F after 8 gate delays. That will affect it. So this is known as the propagating through the gates, and the delay related with that propagation. So if you look at over here, this is like a typical inverter example. The input, when it goes to the 50%, is changing to the high, and the output we start to see the 50%, which is going to go low. That is known as high to low transition, first sense. And on the second one, this is known as low to high transition, because that's going low and the input is changing to high. So to find the propagation delay, we normally take the maximum of these TPHL and TPLH values, and we can find the worst case consideration for the propagation of a single inverter. So this is one of the important things that we normally take care when we design circuits. The propagation delays are also important. Now we are going to do a couple of examples, and we will get into the details of the timings of the flip-flops, which we haven't seen it before. So example says, an integrated circuit logic family has NAND gates with a fan out of 8 standard loads and buffers with a fan out of 16 standard loads. So NAND gates with a fan out of 8, and the buffers with a fan out of 16 standard loads. Sketch a schematic showing how the output signal of a single NAND gate can be applied to 38 other gate inputs using as few buffers as possible, and assume that each input is one standard load. Now in total we need to have 38, so our NAND gate has to drive 38 loads. Now each of these buffers can fan out of 16 standard loads. That means we can divide this into 3. Now we can have a buffer on these signals, so if I have one buffer, that will give me 16 inputs. Then if I have another buffer, that will give me another 16 inputs. Now I have got 32 that I can derive. Now what left? We have just left with 6 of them, so this can be directly derived from NAND gate itself. So in total I can derive 38 by the help of these buffers, and we can have 38 gate inputs derived by a single NAND gate. I hope this is clear. This is pretty straightforward. If you have any question, please do not hesitate to ask me. Now the next example, it says assume that the propagation delay is the average of TPHL and TPLH. Find delay from each input to the output in the below figure by finding the TPHL and TPLH for each path. Assuming TPHL is 0.20 nanoseconds and TPLH is 0.36 nanoseconds for each gate. From these values, find average delay for each path. Now when we consider the paths, we have got one path from C or D to the F, we have got another path from B prime to the F, then A to the F, and B C prime to the F. So these are all the paths that we need to consider when you want to calculate the average propagation delay. Okay, let's start with the first path, which is C, D to F. In the first path we have got 1, 2, 3, 4 stages or 4 gates. So that means we'll need to have 4 TPHL plus 4 TPLH divided by 2 to find the average. So that means 4 times TPHL plus 4 times TPLH divided by 2. That is 4 times 0.20 plus 4 times 56 divided by 2. So 0.80 plus 1.4 divided by 2. That's 2.24 divided by 2. Have 1.12. So that's the TPD for path C or D to F. Then we repeat the same thing for B prime to F. B prime F, we have got 3 stages, so that means we will have 3 times TPHL plus 3 times LH divided by 2. So 3 times 0.20 plus 3 times 6, that's 0.60 plus 1.08 divided by 2. 1.68 divided by 2 give us TPD from B prime to F as that's B to F, B prime to F. Then we repeat the same thing for A, B and C prime because they have just got one stage, 2 stages including their the F. So 1, 2 or 1, 2, we can say that A or B or C prime to F. In this case we have got 2 stages, 1, 2 or 1, 2. That means we need to have 2 times PHL plus 2 times PLH divided by 2. And that is equivalent to 2 times 0.20 plus 2 times 0.36 divided by 2, 0.40 plus 0.72 divided by 2, which is equivalent to 1.12 divided by 2, that is 0.56 nanoseconds. So for each path we have calculated the average propagation delay for the combinational circuitry. The next thing that we are considering in this chapter is about the sequential circuits. This is really important because we have seen sequential circuits, flip-flops and the latches, but we haven't seen the timing properties of the flip-flops. Now, when we consider a flip-flop, we need to consider a clock. So clock is a train of pulses, and based on the rising edge or the falling edge of that clock, we perform an operation through the flip-flop. So either it becomes transparent or it just performs something. So that rising edges and falling edges is somewhere here. Okay, so let's take it rising edges only. With the flip-flops, when we got the data coming in, let's say this is our data line, start with 0, stay 0, change it to 1 and stay 1. This is our D. When we consider the flip-flops, the most important thing over there, D must be ready before it gets into the rising edge of the clock. So it has to be ready sometimes over here before the rising edge, or maybe somewhere here for the rising edge. So this duration for the rising edge, it's known as TS. So before the rising edge, we need a short amount of time. Our input must be stable. So we must have a valid input before the rising edge of the clock. That TS is known as setup time. So we need to have a setup time. On the other hand, after the clock rises, we need to have a short amount of time. The input has to stay stable. This is known as T hold. So the hold time. So before the rising edge of the clock, we need a short amount of time that our input needs to be stable, and after the rising of that clock, we need a short amount of time to hold the valid input over there. Okay? And this is known as setup time and the hold time. Descriptions are given, as I already stated. Now, if the input comes later, so it comes when the clock is changing from low to high on the rising edge, this is a setup time failure. Or if the input changes suddenly after it rises, when the clock is rising, then this is a hold time failure. So when we consider sequential circuits, we have to do analysis related to these to avoid this setup time and hold time failures. The next thing that we are going to consider in flip-flop timing is the propagation delay. Propagation delay, it's related with the clock to the output. Now with the propagation delay on the first rising edge of the clock, we need to expect some output. So our input is 0, that means for a D-type flip-flop, output is going to be 0 as well. Stays 0 until the next rising edge. That will change to 1, stays 1. This is our Q. When we consider the propagation delay, whenever the clock starts to rise, we start to see a change on the output. And that change can be summarized in two parameters. One of them is the first reaction of the output, which is known as TP in or TO. And the second one is known as that the output has to be stable. So this time is known as TP max, maximum propagation delay. When we consider the propagation delay of the flip-flops, there are two of them. One of them is the maximum, that the output has to be stabilized when the clock edge is changing. And the minimum one is the output's first reaction for the clock change. And this can also be summarized, the definition over here, the time interval between the triggering clock edge and the stabilization of the output to any value. Same parameters can be summarized as two values, TP max and TP min, as we already said, the maximum and the minimum propagation delay times respectively. And this is TP min is also known as the contamination delay, maximum clock to out delay, or the minimum clock out delay. And we can also see the similar waveform for the clock. So as you can see, setup time is before the rising edge and the hold time is after the rising edge. So we need short amount of time on both sides. So we need to have the total TS plus TH when we want to consider the timings of the flip-flops, the valid input. And then we have got the TP min as the first reaction of the output to the clock edge, and TP max, the stabilization of the output, is the maximum time that we can have. As we already said, the data input is not allowed to toggle between these timings, and the output can show up sometime between TP min and TP max, and there's various reasons for that. It can be a different vector or different operating conditions, or maybe the device variations that we need to consider. As we already said, we need to have a valid input before the rising edge and valid input after the rising edge. And we said that if there is no valid input, if it's changing while the rising edge, I'd have a setup time failures and hold time failures. So to avoid these failures, we need to do analysis related to these. So we need to check the sequential circuit as a whole so that we can ensure that the setup time and the hold time requirements are all satisfied. So how do we do that? We need to have an Fmax or setup analysis. Fmax is the maximum frequency that we can, operating frequency that we can have. To find the maximum operating frequency, we need to find the minimum period for that clock. Duration of the complete cycle based on the given flip-flops, the combinational logic in the path, and so on. And when we find the minimum period over there, we can just use the frequency calculation and we can find the higher operating frequency, which results in higher performance. And the minimum period is determined by the longest delay. That's what I'm trying to say. So from one path to the other, which we have got a couple of flip-flops or maybe the combinational circuits, we need to find the longest delay over there. So that longest delay will actually going to give us the minimum clock period that it is required, because we need to cover all those in the path. We are going to do an example, and I think it will be more clear when we do that example. Each path delay has three components. In one flip-flop, which is sending or transmitting the data, which has got its propagation delay, and we are considering the worst case delay, so we have to consider the maximum propagation delay. Then we have got the combinational logic delay, which is normally known as TPD-COM. It can be ALU, other multiplexer, something over here. And of course, we need to have the receiving flip-flop setup time, because we have to have got that ready before the rising edge of the second flip-flop. That means we have to consider the setup time of that as well. This can be shown in the timing waveform as well. When the clock starts on the first rising edge, we'll have the propagation delay of the flip-flop 1, so TPD flip-flop 1, which is the maximum in this case that we are going to get. Then we have the combinational logic propagation, because it has to propagate from input to the output. Again, we consider the maximum, and that has to be greater than the setup time of the flip-flop 2. So this timing has to be ready before the rising edge of this clock. We need to have that those two to be greater than the setup time. So how do we write that? We can write that as setup equation. So the setup equation tells us that T period min minus propagation delay of the flip-flop 1 plus propagation delay of the combinational logic has to be greater than the setup time of the flip-flop 2. Now, the amount of time that we need to have the total of flip-flop 1 propagation delay and the combinational logic, when we subtract it from the complete period or the cycle of the clock, it has to be greater than the setup time, otherwise we'll have setup time failure. So we can say that if the input to a flip-flop doesn't stabilize in time before the rising edge of the clock, we have got a setup violation. Once again, if the input to a flip-flop doesn't stabilize in time before the rising edge of the clock, we'll have a setup time violation. We also have hold time analysis apart from the setup analysis, and we need to have the hold time analysis, and we need to do that because we don't want to have a hold time failure. And for the hold time failure, if the input of the flip-flop doesn't stabilize in time after the rising edge of the clock. So for the setup time, it has to be before the rising edge. For the hold time, it has to be after the rising edge of the clock. Then we have got a hold time violation. It can be the smallest propagation delays that can cause the hold time violation, so that we need to consider the minimum delays in the path as well. So when we look at the timing diagram, on the first rising edge, this is changing, so we observe that from the setup analysis, going through that. On the hold time, we have to observe when the rising edge of the clock, the minimum delay of the flip-flop 1 has to be considered, the minimum delay of the combinational logic has to be considered, that they are both has to be greater than the hold time of the flip-flop 2. So we can say that the hold equation have TP mean of the flip-flop 1 plus PD mean of the combinational has to be greater than the hold time of the flip-flop 2. These are the two important equations that we are going to use for the rest of these timing calculations that we are going to consider in the couple of sections. There is another parameter or the consideration that we need to take care is the slack. So slack is actually the margin. We need to have some kind of margin for the setup and the hold time that we are allowed to get the shortest delay or allowed to have a maximum delay over there for depending on the specifications. Now the setup slack, it's related with the setup equation that we have seen. So to find the slack setup, we need to have the period minus the equation that we already had it for T setup equation, the flip-flop propagation delay, the maximum, the combinational delay, plus the setup time. So when you subtract these three from the period, if the result is 0, that means our clock is okay, and we are in the margin, and we don't need anything extra, or we don't need to deduct, or we cannot check. I mean, we can say that it's going to work. But if there is a negative slack over there, that means the circuit is not going to work because our clock is too fast. So we have to slow it down. We have to add something to the pad, or we have to slow down the clock. On the other hand, for the T hold slack, we need to consider the minimum propagation delay of the flip-flop 1 and combinational logic, and we have to subtract the hold time from it, because we need to have that data to be valid when we have got the rising edge of the clock afterwards. So we'll do an example, and I think with an example it will be much more easier to understand. Example 3 says, assume all flip-flops in a sequential circuit have propagation delay of 0.2 nanoseconds and the setup time 0.1 nanosecond. Also, assume the largest combinational propagation delay is 1.3 nanosecond. What is the slack setup if T period is 1.5 nanoseconds? Now I have got all the things that is necessary. So the flip-flop propagation delay is 0.2 nanosecond and the setup time is 0.1 nanosecond. In the combinational logic, I've got the propagation delay of 1.3 nanosecond. The period is 1.5 nanosecond. Now, when we consider T-slack setup, we need to have T period minus TPD of the flip-flop plus TPD of combinational logic plus T setup of the second flip-flop. So now we can say that 1.5 is our period minus TPDF is 0.2 nanosecond plus TPD combinational logic is 1.3 nanosecond plus the setup time is 0.1 nanosecond. So that is equivalent to 1.5 nanosecond minus 0.6 nanosecond. And that is equivalent to minus 0.1 nanosecond. So we have got a negative slack over here. What we can say about negative slack, that means circuit is not going to work because the frequency is quite fast and we have to slow down the clock period. So as we have got 0.1 nanoseconds and what we are expecting is 1.6 nanosecond, that means we need to have 1.5 plus 0.1, 1.6 nanoseconds. So we have to slow it down for 0.1 nanoseconds. So we need to make it 1.6 nanoseconds so that this circuit is going to work. And this is example 3 solution. Another important thing when we consider the sequential circuit is the clock skew. Clock skew is when we have a multiple flip-flops and they're all have supplying the same clock, but from the first clock to the second flip-flop we might have some delays. That delay, it might be because of the buffer on the path or it might be because of the long wirings. So when we consider this type of circuits, we need to consider the skew of the clock because there will be a short delay. We need to add this delay into our setup and hold time equations so that they have to be considered throughout the circuit. And in order to do that, we modified the setup slack and hold slack equations. It's similar, so T period minus TPDF 1, the flip-flop propagation delay 1, the combinational logic, the setup time of the second one, minus the clock skew. So we have to subtract the clock skew from this path because this is actually supplying the clock later on. And for the hold, we just need to subtract the clock skew from the complete equation. Now, there are two things over here. The clock skew on the setup slack, as this is subtracting and that is also subtracting, this is actually going to help the slack. But for the hold time, this is going to hurt the slack because there will be a delay and we need to avoid that delay because of the clock skew. So we might have some hold time failures. Consider these skews. We are going to do an example related with that as well. We have to be careful. Next example shows over here. Example 4, we have got a flip-flop 1 and the combinational logic and the flip-flop 2, and of course we have got a buffer on the clock path, so there will be a skew of 1 nanosecond from the flip-flop 1 to flip-flop 2. So for both flip-flop 1 and 2, setup time, hold times, the minimums and the maximum propagation delays are given. The combinational logic maximum delays are given and the minimum. Check for any timing violation, it says. Now, before we get into the calculation, we can show the timing waveform. So the clock of the flip-flop 1 is running, which is 100 megahertz. We need to have 10 nanosecond period for 100 megahertz. So the setup, the propagation delay of the flip-flop, first flip-flop is 2 nanoseconds for the minimum and 3 nanoseconds for the maximum. Then we have got the valid output data over there. And then we have got the flip-flop 2, but flip-flop 2 will have a skew because of the buffer. So 1 nanosecond will be delayed from flip-flop 1 to flip-flop 2, as you can see. Now we have got the combinational logic maximum propagation, and we also have the delay of the flip-flop 1, and of course the setup time of the flip-flop 2. So in total we have got 8 nanoseconds till the second rising edge of that clock. Then we have got the rising edge of that clock, which is skewed clock for D2, and there will be a minimum propagation delay of 2 nanoseconds. Then we need to have the 4 nanoseconds for the output to stabilize, and we have got 6 nanoseconds beforehand. Now let's do the calculations for the setup slack and the hold slack. So T slack setup, we need to have the period minus the flop 1 the combinational logic plus T setup of flip-flop 2 minus T clock skew. That we need to take it into consideration. So that means our period is 10 nanosecond minus TPD flip-flop 1 is 3 nanosecond, and the combinational logic maximum is 2 nanosecond, plus the setup time of the flip-flop 2 is 3 nanosecond minus 1 nanosecond, which is equivalent to, it over here, 10 minus 7 nanoseconds give us 3 nanoseconds. So we have got 3 nanoseconds for the setup slack. Let's do the hold one as well, then we'll talk about it. T slack hold. Then we have got over here TP minimum of the flip-flop 1, TP min of the combinational logic, minus T hold time of the flip-flop 2, minus T clock skew. So that is equivalent to the minimum of the flip-flop 1 is 2 nanoseconds, plus minimum of the combinational logic is the 1 nanosecond, minus the hold time of the flip-flop 2 is 3 nanoseconds, minus 1 nanosecond for the clock skew, which is equivalent to minus 1 nanosecond. Now the question that we need to ask, as we have got the setup slack as 3 nanoseconds and the hold slack as minus 1 nanosecond though. So minus 1 is going to be a problem because we have got a negative slack over there. And the question is, how do we make this design work, or the fixed timing at 100 megahertz? So as we have got a margin for the setup, which is 3 nanoseconds, actually delay the data. So how do we delay the data? We can delay the data from the flip-flop 1 to the flip-flop 2. How can we do that? We can add a buffer, because each buffer is 1 nanosecond. We can add 3 buffers, and we can have that 3 nanosecond buffer delay can be covered. So when we add 3 buffers over there, 3 nanoseconds will avoid any setup slack margin, and this will be 0 as we are going to add through the path. And for the hold slack, as we have got minus 1 nanosecond over there, and that's because of that skew of the clock, because of the buffer. What we can do is we can rearrange the wiring of the clock so that we can avoid this buffer on that line. So when we avoid that buffer on that line, this will be equivalent to 0, and we will not have any problem. So we can route it differently. And that was the end of example 4. I hope it is clear, and if you have any question, feel free to ask. Now we have got another example, circuitry with a lots of different timings. We have got ALU, a multiplexer, flip-flops in the path. So we can say that we can go through each of these, because we have to go through each of these to find if there are any setup slack or hold time slack, and we have to identify a solution for it. And all the AC timing specifications are given to us. There are no delays in the wires themselves. Input in shows up to 4 nanoseconds before and hold until 3 nanoseconds after the rising edge of the clock. And the same clock is routed to all registers, so there's no clock skew, which is good, and they all arrives at the same time. Now it says identify any hold time violations and find Fmax. So we have to find both the setup and hold time violations through Fmax and hold time violation analysis. We can identify the paths. So for example, path 1 is from R1 to R4, path 2 is R2 to R3, and path 3 is R4 to R5, path 4 is R3 to R5, path 5 is R5 to R6, and path 6 is R6 to R1, and path 7 is R2 to R4. Now we need to analyze individually for each of them and find out their Fmax and the hold time violations. I'm gonna go from the slides. Let's start with the path 1. For the path 1, we need to have R1, Fmax, we need to have R1 propagation delay, the maximum, the ALU's propagation delay, and R4's setup time. And for the hold time violation, we need to have R1's minimum propagation delay, the propagation delay of the ALU, minus the hold time of the R4. So now, from R1 to R4, the maximum of R1, the ALU, and the setup time of R4. And for the hold, we have got the minimum of R1, ALU, and the hold time of R4 has to be subtracted. That's 17 nanoseconds, and that is 9 nanoseconds. So there's no problem. We'll carry on. So the path 2 is R2 to R3, and here we need to have the maximum of R2 and plus the setup time of R3. We don't have any combinational logic in between, so this will give us 6 nanoseconds, and the hold time is the minimum of R2 minus the hold of R3, which will give us 2 nanoseconds based on the parameters given. Now we need to go to the path 3. Path 3 is R4 to R5, so we need to have the maximum of R4 plus the multiplexer's combinational logic delay and R5's setup time. That will give us 10 nanosecond. And then we repeat the same thing for the hold, the minimum of R4, the max propagation delay, and minus the hold time of R5, which will give us 6 nanosecond delay. And path 4 is R3 to R5. Then we need to have the maximum of R3, the propagation delay of multiplexer, and the setup time of the R5. When we add them together, that's 9 nanosecond. And for the hold, we need to have the R3 minimum delay, the max's propagation delay, and R5's hold delay has to be subtracted, which will give us 4 nanosecond. Then the path 5 is just from R5 to R6, and this is going to be the maximum of R5 and the setup time of R6, which is 7 nanoseconds, and the hold time is the minimum of R5 minus the hold time of R6. Over here, as you can see, we have got minus 1 nanosecond, so we have got a negative slack from that one to there. So that means we'll have a hold time violation, which is a timing failure, and we have to fix that. So let's keep that one over there and carry on. For the path 6, we need to have R6 to R1. We have got R6, the maximum propagation delay. Then we have got 4 buffers in the path we have to consider, and the R1's setup time, which will give us 14 nanosecond. Then the hold, we have got the minimum of R6, then the 4 buffers on the way that we need to consider minus the hold time of R1, which will give us 10 nanosecond without any timing failure. And the last one is the path 7. So R2 to R4, we have got R2 max plus the ALU's propagation delay plus the setup time of R4, which will give us 18 nanosecond. And the hold time is the minimum of R2 plus the propagation delay of ALU and minus the hold time of R4. Now that will give us 11 nanosecond. So the Fmax, when we consider, we have got 7 paths. From the 7 paths, we have got 17 nanosecond, 6 nanosecond, 10 nanosecond, 9 nanosecond, 7 nanosecond, 14 nanosecond, and 18 nanosecond. So the maximum largest delay that we have got in the path is from R2 to R4, which is path 7. So when we consider, we can consider the period based on that. So that period, 18 nanoseconds, 1 over 18 will give us 56 megahertz clocks for the maximum possible operating frequency. And we can say that path 7 is the speed limiting path for this design. How about timing failure? For the timing failure, we need to be fixed that one because we have got minus 1 nanosecond timing failure. And as we have got plenty of setup slack on these routes between R5 and R6, what we can do is we can add a buffer in between of these. So if we add one buffer in between of these, we can avoid the setup slack as well. This will be 0 as we added a one buffer over there, and this will be 8 nanoseconds in total. So that will solve us out with the path 5. I hope it's clear and I hope it makes sense on how we are calculating these paths. Note down if you have any question and ask me during the question and answer session. Now the next thing that we are going to consider in this chapter is the asynchronous interactions. So interactions that are not synchronized with the clock is an asynchronous interaction. So what we can have is, we can have a synchronous circuit, we can have an asynchronous circuit, and you want to send something from synchronous to asynchronous, we might have some combinational hazards. So we need to take care of these hazards because it might cause the circuit not to function properly and we might not get the output that we are expecting. Have a various circuit topologies like asynchronous circuit to synchronous circuit. We have got an asynchronous signals going on over there, or synchronous circuit to synchronous circuit. There might be some asynchronous signals and they have both different clock frequencies, so this might cause a problem, and that problem is called metastability. So the metastability is one of the outputs or the signals staying either between 0 and 1 for a long time. So it's not a valid logic level 0 or valid logic level 1, it's in between, and we call it metastable circuitry, and we have to be careful over there. So when we consider a typical example, which is a K-map shown over here, so we can just cover the ones, and we have got the expression for it, which we can implement it with the NAND gates. If we think about this circuit implementation, we have got x1, x2, or x2 prime y, which is given over here, and when we want to implement it with NAND gates, we just need to take the De Morgan of that so that we can have that circuitry implemented. Now, up until now, we don't have any problem because we have seen these and we know how to implement it. Now, assume that each gate has a delay of 1 unit, including the inverter as well, and x1 and y is equals both 1, and x2 is transitioning from 1 to 0. So x1 and y both are 1, That's what we have set. And x2 is changing its transition from 1 to 0. Now, A should be the opposite of x2, but we need to take care of the timing. So at time 0, x2 is changing from 1 to 0. These are staying high. Then A is going to change on the next time, because it starts to affect that one on the next, because we have got a delay of 1 unit over here. That means we need to wait for 1 unit over there. On the next clock, A is changing. Because it's inverted, that's at 0, that has to be 1. So up until now, we don't have any problem. Now, let's see C and B. Now, at the beginning, as we have got a 1 unit of delay, x2 is going to change. So at the beginning, this is 1 and 1. So when 1 and 1, we have got the NAND gate, which is output C, is going to be 0. Because x1 and x2 is 1, output is 0, without any problem. Then B over here is going to be inverted. So A is 0 and Y is 1. So 0, 1 will actually give us 1 for the NAND gate. And so over here, we all have the valid outputs and the inputs. Then after the first clock or the first timing that we have got the delay, this is changing and we have got x2 to be 0. So 1 and 0, the NAND will give us what? It has to be 1. But now, as this is changing, and we need to wait 1 clock delay because of the NAND, we are going to see the change over here. Okay, so we have to delay it. When it's changing over there, then we need to wait 1 unit delay to see the change over there. And for B, this is going to be A and Y. So A is 0 over there and Y is 1 and B is 1. But as A is changing on the next, so 1 is over there, 1 is over there, then on the last cycle we start to see the change of B. Now then C and B is going into another NAND gate for F, and in that case, as B and C is going in, so 0, 1 is 1, 1, 0 is 1, then 1 and 1, it's 1 over there, and then we have got 0, 1, which is 0 over there. This is because we have got a 1 unit delay, and 1 and 1 of that has to be 0 over there. So this is actually showing us static 1 hazard. So static 1 hazard occurs when there are 2 adjacent ones in a K-map of F not covered by a single loop. So if we look at over here, we have 2 adjacent ones which is not covered by a single loop. Now, to avoid that static 1 hazard because of the unit delays, we need to have that combination as well. I know it's redundant, but to get rid of that static 1 hazard, we need to combine those 2 ones together as well. We'll have an extra expression over here with an extra gate probably, but this will avoid the hazard in the circuitry. And static 0 hazard, which is the opposite of static 1 hazard, occurs when there are 2 adjacent ones in a K-map of F prime. So this is for the K-map of F, and if we have adjacent ones and not combined. For F prime, if there are 2 adjacent ones and not combined, we'll have static 0 hazard. So to fix the previous example over here, we need to combine these 2 ones together. Then we will have another expression, which is x1 and y, which is this one, and that will be added in the game. Now we are having a hazard tree expression, but with a redundant expression over there. So hazard is removed and we have to be careful. So how do we design hazard-free combinational network? When drawing loops on a K-map, ensure each adjacent pair of ones is covered by at least one loop, which we already done. And if there is no problem with the cost, so you can have a larger circuitries over there, a brute force method of obtaining hazard-free network is the sum of all the prime implicants of the logic function. So we can combine all the ones, even with the redundant ones, and we can have an hazard-free circuitry. But in this case, we'll have a larger circuitry. If the cost is a problem, we have to be careful over there how to balance it. So when manipulating the result, the algebraic expression, do not use x prime plus x which is equals 1 or x prime dot x which is equals 0 or any similar equations over there. You can use distributive law or the De Morgan's law to simplify it, but if you are using that, you might get rid of a node and it might cause a hazard in the network. Right, let's consider metastability. So metastability is the ability of a digital system to persist for an unbounded time in an unstable equilibrium or metastable state. So the memory cell over here is a bistable circuitry because we have got a Q1 to be 1 and Q2 be 0 in the case, or Q2 to be 1 and Q1 to be 0, and there are only two stable states. But the transfer function, as you can see for a memory, it can be seen that it's going to oscillate. So it can occur when two asynchronous signals combine in such a way that their resulting output goes to an intermediate state, and output oscillates between 0 and 1, and it can have a metastable state in between. Now metastability can occur in sequential circuits because of the asynchronous signal, and whenever the input signal does not meet the setup time or the hold time of the flip-flop, it can cause a metastability problem. And theoretically, metastability for the memory cells like the latches or the flip-flops, it can stay in there indefinitely since they're in equilibrium. So in practice, like the noise event or the imbalance between the circuit flips, the result to a high to a low voltage, so in an infinite time. So sequential circuits metastability may cause long input to output delays, and because the flip-flops that switches, it might switch late or doesn't switch at all. To get out of the metastable state, what we need to do is we need to either force the flip-flop to be into a known state using the signal specifications, or we have to wait long enough. We can also use synchronizers, which is a sequential circuitry where we have got flip-flops cascaded. Now with the synchronizers, the asynchronous input can come in, but after a couple of flip-flops with the clock, it can be synchronized. So generally, the best way to have it is a 3 or 6 flip-flops in cascaded version. But the problem is they never remove it 100%. So we will still have some small amount of metastability. And we need to take care of the flip-flops that they are switching. There won't be any combinational delay in between them. Finally, the last example that we have, for the following logic expression, find all the static hazards in the corresponding two-level AND/OR circuit and design a hazard-free circuit that realizes the same logic function. If we do that, f is going to be wx plus w prime y prime. Now, the K-map shows us 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and this is y, and this is w and x. So we have got wx, which is 1 and 1, and we have got W prime Y prime, which is that one. Now, in the normal conditions, what we generally do, we combine these two, which will give us W and X, and we combine these two and we get W prime Y prime. So to avoid the static hazard, we also need to combine these two. So this will give us X Y prime. So this will help us to reduce the static hazard in this circuitry. Now that's the end of this chapter. If you have any question or if you have any problem with this chapter, please note it down and you can ask me during the question and answer session. Thank you very much.